Howdy, howdy, this is Mr. Potter. In today's video, we're going to talk about transforming our functions. So we've been dealing with parent functions. We've talked about how important parent functions are. And what's really nice about parent functions is that through the transformations that we learned in our geometry class, we can actually do quite a bit with them. So in today's video, we're going to talk about translations and reflections. These actually belong to the family of isometries. Isometry comes from the Greek, which means equal measure. And so what we're talking about transformations that don't change distances. So for our purposes, when we talk about isometries, there's really three of them that we talk about. We talk about translations, we talk about reflections, and we talk about rotations. And in today's video, we're going to be primarily talking about these two. So keep in mind that when I'm talking about a translation, I'm talking about moving something up or down or right or left or some combination. So I could move it up and to the right, or I can move it down and to the right. When I talk about a reflection, I'm going to have some line that's going to act as an axis of symmetry, and my shape is going to get reflected over here, but the distance between the points are all going to be the same. When we talk about rotations, which we'll talk about tangentially at the end of the video, we're basically talking about how if I have some type of shape here, that this shape actually gets rotated around some angle to get to its new position, but these distances are all going to be the same, and I can rotate the shape again and so forth. So there's one other transformation that we will be talking about in our next video, but it's not an isometry. And that's a dilation. And a dilation you can think of as a stretch or a shrink. But we'll really be talking about that more in tomorrow's video. Today, we really want to emphasize on translations and reflections. So the first thing I want to talk about are vertical shifts. In other words, taking a graph and moving it up. So imagine that I have some graph, and it could be any shape. But if I want the net effect is to take this entire graph and move it up a unit, I basically want to take each point and move it 1 point higher than it was. That gives me the effect that I'm looking at of a graph that's been shifted up 1 unit. In other words, if this graph is f of x, what I really want to do is really say that g of x, my transformed graph, is whatever f of x is plus 1 unit. In other words, the y-coordinate here is really 1 more than the y-coordinate here. The y-coordinate here is really 1 more than the y-coordinate here, and so forth. That is our transformation. So when we're talking about vertical shifts, the net effect is to add or subtract to our function. In other words, to go up, we're really looking at g of x being equal to f of x plus some constant value k. So this goes up k units. And if I want to go down, then I want g of x to be equal to f of x minus k. And this would go down k units. Because if I wanted to take this white graph and move every point down 1, 2 units, 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 I would end up with a graph that looks kind of like this. So we can transform by either adding or subtracting to whatever our original function is. So let's do a couple of examples of this. So let's say that I have my parent quadratic function, and I want to take this quadratic function and move it up 3 units. So graphically what we're talking about is we know our quadratic function passes through the origin, passes through the point 1, 1 and 2, 4, negative 1, 1 and negative 2, 4. So we end up having this curve. And if I want to add 3 units to each of these points, that means instead of passing through the origin, I'm really passing through the point 0, 3. Instead of going through the point 1, 1, I'm really going through the point 1, 4 and negative 1, 4. And instead of going through 2, 4, I'm actually going through 2, 7. So I'm actually getting into the word problem part of this. So if I were to take each point of my graph and add 3 to it, that would transform the graph by raising it up 3 units. So if f of x, my yellow graph, is x squared, my parent function for the quadratic, then g of x, my transformed function, is going to be x squared plus 3. Now, do you have to go through all of this? Well, it depends on what the question's asking. If the question wants an algebraic expression, you really can just go ahead and just say, oh, plus 3, and take care of it that way. If, however, it's asking for a graph, then you're going to have to take each one of our characteristic points, and a parabola usually has at least 3 of those, and we're going to have to translate each of those 3 points up by however many units. So let's do one more example of this. I want to take the parent square root function and move it down 4 units. So if f of x is equal to the square root of x, then g of x has to take that exact same function, whatever f of x is, and subtract 4. Because that's going to take each one of these square root values and move it down 4 units. Now, of course, remember that my square root function has this restriction that x has to be greater than or equal to 0. This is my domain. So I need to keep that in mind when I'm looking at the graph. So I could say that g of x is equal to the square root of x minus 4. Or I could say it's equal to negative 4 plus the square root of x. And some people would prefer to write it this way because otherwise it's a little confusing sometimes, especially if you write it quickly. So just be aware, you probably want to write it as unambiguous as possible. So that's what I'm doing with that minus 4, either putting it at the end completely far away from the radical or putting it in front. So if that's a vertical shift, then I want to talk about a horizontal shift. So let's talk about some function like y equals the I don't know, how about y equals x? So if I take this graph here, y equals x, and I know y equals x is going to pass through the origin, the 1, 1, and 2, 2, and 3, 3, and negative 1, negative 1, and negative 2, negative 2, and negative 3, negative 3. If I want to move this to the right, then what I need to do is I need to actually get some point over here, and over here, and over here. All of these points that I just plotted, I really need to move them over to the right. And so in doing that, if I move it over to the right, then I'm really saying that I want this to be 0. In other words, g of x really needs to be 0. But keep in mind, x is 1. So the question is, if it's a linear function, how do I get equal to 0 when x is 1? And the easiest way to do that is to subtract 1 from inside the parentheses. In other words, if I want to move something h units to the right, I'm going to have to say that g of x is equal to f of my function x minus h. And it's important to note that the sign that we see here is going to be the opposite of what we think should happen. Normally I think numbers to the right, well, the right is where my positive numbers are, so I should be adding something. In reality, we subtract something because we want to know what are we going to have to do to make this expression equal to 0 or equal to whatever the previous value is. And so really what I've got is y equals x minus 1 is a shift 1 unit to the right. Now some of y'all may be noticing, hey, isn't that just a shift that's 1 unit down? Well, yeah, it is. And the thing is, sometimes it's going to be ambiguous as to which shift we're talking about. But in this case, it's only ambiguous because this pink line that I've drawn really is two things at once. It really is a shift 1 unit to the right, and it really is a shift 1 unit down. But in general, we're always going to have this horizontal aspect, this horizontal subtraction inside the parentheses. In other words, it's going to be much more intimately involved with my independent variable than my dependent variable. Keep in mind, when we were talking about vertical shifts, we were really talking about taking the y value and adding 3 to it, because adding 3 to the y value moves stuff up 3 units. In this case, because I want to move horizontally, come on, there we go. Because I want to move horizontally, I want to deal with this independent variable. And it ends up being the opposite of what I'm expecting. In other words, to move h units right, then g of x has to be equal to f of the expression x minus h. And to move h units left, then g of x is going to be equal to f of the expression x plus h. Notice that even though I'm moving to the left, this is still a plus sign. Even though I'm moving to a right, this is a minus sign. We have to keep in mind that when we're dealing with horizontal shifts, that it's going to be the opposite of what our common sense tells us. So let's do a couple of examples here. The first thing I want to do is I want to take the cubic parent function and move it 5 units to the right. Now keep in mind that if I'm doing 5 units to the right, then h is 5, and I want to subtract. So normally g of x is going to be equal to f of the expression x minus 5. For us, our expression is x cubed because it's our parent function. That's what f is. So if f of x is x cubed, then f of x minus 5 is going to be the expression x minus 5 cubed. Similarly, if I want to take the absolute value parent function and move it 2 units to the left, keep in mind because I'm moving it 2 units to the left, h is 2. And because I'm moving it to the left, we are going to add. So for us, g of x ends up being f of the expression x plus 2. And here, f of x is our absolute value function. So for us, g of x is going to be equal to the absolute value of the expression x plus 2. And what this does is it actually graphs it 2 units to the left. If I were to take a look at it from a table, -2, -1, 0, 1, and 2, if I substitute -2 in for x, I'm going to get 0. If I substitute -1 in for x, I'm going to get a positive 1. In other words, I'm really ending up with just the right half of that v. So what happens when I do a -3? Well, -3 plus 2 is -1, and if I take the absolute value of it, I get 1. So in other words, normally my graph would lie here, centered at the origin. But because of this shift 2 units to the left, my origin is really here at x equals -2. -1 gives me a positive 1. 0 gives me a 2. So this is the right branch of the absolute value. -3 gives me a 1. So this is my left branch of absolute value. And notice what's happened is that this v that we had here, our original parent function, has been shifted 2 units to the left. So it's important to know that when we're talking about a shift, when we're talking about a translation, it really involves just adding or subtracting a constant value. What's important to distinguish is that moving up or down means that we're adding the value to the y expression. In other words, we're adding the value to f of x. If I'm moving to the left or the right, there's 2 things we have to keep in mind. One is, because I'm moving to the left or the right, I'm dealing with my independent variable x. And so I'm really dealing with inside the parentheses of f of x. And 2, it always ends up being the opposite of what our common sense would tell us. In other words, moving to the left adds, moving to the right subtracts. So that's translations. Let's talk about reflections now. Reflections are a little bit easier. So basic reflections we're going to be talking about is if I wanted to reflect across one of our axes. So in this case, because I'm talking about a vertical reflection, I want to talk about reflecting across the x-axis. In other words, this x-axis is going to act as a mirror. So if I have some curve up here, I need to make sure that its mirror image is going to be the same distance away from that axis. And so what happens is values that were positive become negative. And because of this, I would have to say that g of x is equal to the opposite of f of x. In other words, -1 times f of x. And so to do a vertical reflection, a reflection across the x-axis, we're going to say that g of x is going to be equal to -1 times whatever my original function is, f of x. So I want to do a couple of examples of this. So let's say that I want to reflect the linear parent function across the x-axis. Well, normally the linear parent function would just be y equals x. And I know that the linear parent function is going to look like this. So if this is f of x, which is just x, I know that if I want to reflect it across the x-axis, I'm going to say something like g of x is equal to -1 times x, or -x. And two things I want you to notice. One is that if I'm reflecting across the x-axis, all of these first quadrant points are actually going to get reflected into the fourth quadrant. All of these third quadrant points are going to get reflected up into the second quadrant. And two, this pink line that I've drawn has a slope of -1, which actually looks pretty intuitive here. The thing is, because I'm reflecting, I'm multiplying by -1, but multiplying by -1 changes the slope to a -1. So I can see that happening not only graphically, but also algebraically. Second example I want to do is I want to reflect the square root parent function across the x-axis. So for us, f of x is equal to the square root of x. And we know that if we want to reflect across the x-axis, we're going to say that g of x is equal to -1 times f of x. So it really ends up being -1 times the square root of x. Notice, of course, that for our parent function is always in the first quadrant because square roots are always positive. For our reflection, anything in the first quadrant gets reflected to the fourth quadrant. And because of that, all of our values that we're getting out of g of x will be negative. They'll be the opposite of whatever the principal square root is. So now that we've taken a look at what happens if I want to reflect across the x-axis, if I want to do a vertical reflection, the last transformation that I want to talk about today is I want to talk about horizontal reflections. And again, if I'm talking about a horizontal reflection, I'm talking about a reflection across the y-axis. So I'm talking about a transformation that's going to alter the x value. In other words, x values here that are 2 units to the right are going to get reflected over here 2 units to the left. 3 units to the right are going to get reflected to 3 units to the left. So in other words, the sign of my x coordinate will change. So for us, if I want to reflect across the y-axis, then g of x is going to be f of -1 times x. Or sometimes we'll just see it as f of -x. So in other words, what I need to do is, again, because it's dealing with lefty-righty stuff instead of uppy-downy stuff, I need to make sure that I'm dealing with stuff inside the parentheses. Anything dealing with the left or the right is going to be dealing with inside the parentheses. Anything dealing with uppy downy stuff is going to be dealing outside of the parentheses, because it's going to be stuff that's happening to y instead of stuff that's happening to x. So as we've done several times in this video, I want to do a couple of examples to talk about what's happening here. So the first thing I want to do is I want to take the cubed root parent function and I want to reflect it across the y-axis. So for our purposes, f of x is equal to the cubed root of x. And we know that g of x is really just supposed to be f evaluated at negative x. So it's going to be the cubed root of negative x. Now, something I want to talk about here, if I take a look at the graph, my original graph has no restriction on its domain. That's why we made such a big deal about domains, because we're going to keep talking about them throughout this course. That's my original function. This is f of x. If I take a look at what g of x should look like, well, everything above to the right, everything in quadrant 1, should be reflected in quadrant 2. And everything that's in quadrant 3 should be reflected to quadrant 4. But one of the things that you'll notice in this particular situation is that I've really done the same thing. I've really said not only a horizontal reflection, but I've also done a vertical reflection. I really could take this negative outside of the odd cube and really say that it's the negative cubed root of x. So that's something interesting, and we're going to talk a little bit more about this in just a few moments. Last example I want to do of a reflection is I want to take the reciprocal parent function and I want to reflect it across the y-axis. So for our purposes, f of x is 1 over x. And I want to take this and I want to change the argument. G of x is really going to be f of negative x. So it's going to be 1 over negative x. And just as we did before, this is really also equal to negative 1 over x. So looking at our parent function, our parent function is going to have this type of behavior. But anything that's in the first quadrant is going to get reflected across the y-axis to the second quadrant. And anything that's in the third quadrant is going to get reflected over to the fourth quadrant. But in reality, this yellow graph really looks like I just took whatever was above the x-axis and reflected it below the x-axis, and vice versa. So this really looks like both a horizontal reflection and a vertical reflection. And this actually leads into the last thing that I want to talk about in today's video. I want to talk about even and odd functions. Now, so far we've talked about even and odd from the standpoint of polynomials. So if I have f of x equals x cubed, this is an odd degree because 3 is odd. And so what we noticed about this is that if it's odd, then it has certain properties. We noticed that its range was unbounded. Whereas if I take a look at something like f of x equals x squared, this has an even degree. And so it had an even degree because 2 is even. And so we had a restriction in our, ooh, that is ugly. Let me try and draw another straight line. I guess we're not going to be able to draw straight lines tonight. So that's what my parent function looks like. And notice that we do have a restriction on our domain. We really can't go below y equals 0. But what I really want you to notice here is that anytime that I'm dealing with an even function, even functions are going to have this kind of symmetry to it, whereas the left half and the right half are mirror images to each other. So we really say that even functions have y-axis symmetry. It's important to notice that whenever I'm dealing with an even function, we have this y-axis symmetry. In other words, whatever value I plug in over here for this value of x, and whatever value I get when I plug in for this value of negative x, those really should be the same value of y. And so we actually define an even function. An even function is a function f such that f of negative x equals f of x. In other words, substituting a negative inside the parentheses isn't going to change the y value because the y-axis is acting as a mirror. -4 and +4 are going to look like the same y coordinate. And you notice that that's not true for an odd function. For an odd function, this goes up a certain amount and this goes down a certain amount. What we do notice about the symmetry here is that it really almost looks like these points are being rotated around the origin. And we actually call this origin symmetry. So we say that odd functions have odd symmetry. And so we can actually define that by whatever our x-coordinate is over here. Moving x over to the other quadrant really changes its y sign as well. So an odd function is a function f such that f of negative x equals negative f of x. In other words, changing the sign inside the parentheses also changes the sign outside the parentheses. And this is well and good as long as I'm dealing with polynomials. Polynomials are real easy to figure out because if I have an even degree, then I'm an even function. If I have an odd degree, then I have an odd function. The question is, what about all these other parent functions that we've been talking about? Because we've introduced this concept of all these different parent functions. So let's start about something like f of x being the absolute value of x. Well, there's two ways I can look at it. One way that I can look at this is I can look at the graph. The graph is this V shape, and this V shape has y-axis symmetry. The right side and the left side looks exactly the same. But I could also take a look at f of negative x, and that's going to give me the absolute value of negative x. But one of the properties of absolute value is that we ignore the sign, so I'm just going to have a plain old absolute value of x, but that's just what f of x was. So what I have is that f of negative x equals f of x, and so this function is an even function. If I take a look at a function like our reciprocal parent function, 1 over x, I know what the graph looks like. The graph has this part over here because 1 over a positive number gives me a positive number. 1 over a negative number gives me a negative number. And it certainly looks like I've got this origin symmetry going on here. And as we showed earlier, f of negative x is equal to 1 over negative x. But dividing by a negative just gives me a negative. And that's really the opposite of whatever f of x was. So we would say that the reciprocal parent function is an odd function. Now I could take a look at this similarly and talk about the quadratic square, or the reciprocal squared function, 1 over x squared. And what's nice about this is that because I'm squaring the number first and then taking the reciprocal, squaring a real number always gives me a positive number. So I'm always going to be above the x-axis. And I notice that I have that y-axis symmetry. F of negative x in this case is 1 over negative x squared. But taking negative x and squaring it just gives me 1 over x squared, which is really just f of x. And so we're dealing with a function that is even. And of course, the other thing that we notice is that the cubed root function, let me do that in a slightly different color. If f of x is equal to the cubed root function, I know that the cubed root function is not restricted, so it exists over the whole negative infinity to infinity. But if I try and evaluate f of negative x, that's going to give me the cubed root of negative x. And that's really going to give me negative cubed root of x, which is negative f of x. So we get an odd function. Now, a couple of things you'll notice, there's a couple of functions that we have left out. One of them is the square root function. And if I take a look at the square root function, you'll notice that 1 it only exists in the first quadrant. So there is nothing to reflect in the second quadrant. There is nothing to rotate in the third quadrant. And so this has no symmetry. And so we don't say it's even or odd. We say it's neither even nor odd. And the last one that I want to talk about, of course, our last parent function is the exponential function. And one of the behaviors of the exponential function is that it is always positive. Raising a number to a power, a positive number to a power, is always going to give me a positive number. But I don't have reflection across the y-axis. I don't have the y-axis symmetry. And because I never get into the third or fourth quadrants, I don't have any rotational symmetry. So again, we have no symmetry. And so we are neither even nor odd. So understanding how to reflect and how to translate really helps us get an appreciation of evenness and oddness, talking about the symmetries of the graph. And the symmetries of the graph are going to make the graph a lot easier to graph. It's going to make it a lot easier to interpret the values. It's going to make it a lot easier to deal with the domains. And that's why these are essential concepts in pre-calculus. Once again, this is Mr. Potter. Thank you for watching. Have a great day.